All right, so in this video, we are going to be doing section 7.2, which is titled Trigonometric Integrals. We are going to talk about if you have multiple different trig functions of varying powers multiplied together, how do you go about integrating those particular functions? So in this section, there are a couple of different strategies that we need to go over and how we're going to approach these ideas going forward. So the first strategy we want to talk about is what happens if you have a sine function and a cosine function being multiplied together of either the same or different powers. Now, how these strategies work is that depending on the powers of sine and cosine will depend on which of these three strategies we're going to go with. So strategy number one, if the power of cosine is odd, then you can save one cosine factor and use the following identity. Cosine squared equals 1 minus sine squared to express the remaining factors in terms of sine. Now, the ultimate goal here on today is that when you break terms off, you usually want that to be your du term because there's going to also be a lot of U-substitution in this section. So kind of showing you in a mathematical way is that if you've got sine and cosine, if cosine is odd, you will break one of those cosines off, and then you will have to rewrite the remaining cosine functions in terms of sine. Now, that is where the identity will come in. If you have any extra cosines, you want to use the identity cosine squared equals 1 minus sine squared. And then to set up your U-substitution, since you want du to be that cosine term on the end, you need to let u be sine. So you'll rearrange some terms and you're trying to set up a U-substitution. If the other term is odd, so if sine, if the power of sine is an odd function, you're going to do everything exactly the opposite of what you just did. You would instead save one sine factor, and then you have to use a different variation of the Pythagorean identity. You would have to use sine squared equals 1 minus cosine squared in order to express everything in terms of cosine. So kind of showing you the same idea. If you've got an odd power of sine, you would break that off. Then you would have to rewrite the remaining sine terms in terms of cosine so that you can let u be cosine and set up your U-substitution. Now, some people may be thinking, where are these identities come from? So where does this one and this one come from? Well, if you remember back in trig, there is a Pythagorean identity that sine squared plus cosine squared is 1. And then rearranging the terms of this Pythagorean identity equation, that is where these two variations of identities you're going to substitute come from. Now, another thing is that what happens if both powers of sine and cosine are odd? If both of them are odd, you can either do strategy A or strategy B. It doesn't matter, they will both work the same way. My suggestion would be is that if they are both odd, I would take the smaller power and break that off. So if cosine is a smaller power than sine, I would break a cosine off. If sine is smaller, I would break a sine off. It really doesn't matter. That'll just make the numbers a little bit more reasonable. And then the third strategy is probably the one that is a little bit more abstract, is what happens if neither sine or cosine are even or odd, but both of them or one of them is an even function. This is where you will have to use a variation of the half angle identity. So these are not Pythagorean, but we can say that sine squared equals 1/2 times 1 minus cosine 2x. And you can also say that cosine squared is 1/2 times 1 plus cosine 2x. These are your half angle of sine and cosine formulas. These are used when the powers of sine and cosine are both even. Now, there is another variation. Later on, you may have to use a variation of the double angle identity, because if sine and cosine are both even and they are both the same power, So if they're both squared or both to the fourth or whatever it may be easier to use the following representation. Sine of x times cosine of x equals 1/2 sine of 2x. But this identity at the bottom is only useful if both sine and cosine are even and they are the same power. If they're both even and different powers, you will need to use the half angle identities right above. So what I want to do now is I want to do both strategies, and then we're going to kind of go through all of this, and so we can do some examples. So example number 1, evaluate the indefinite integral of cosine to the 6th of y times sine cubed of y. So when you've got sine and cosine being multiplied together, whichever one is odd is the one you want to break off. Well, sine is your only odd power here. So what I'm going to do first is I'm going to break one of the sines off to make that sine squared of y times sine of y dy. Now remember, your ultimate goal is you want this sine of y dy to go away when you do your U-substitution. But the only way that that's going to work is if you can rewrite this sine squared that's left over in terms of a cosine function. That's where you have to use the variation of the Pythagorean identity. So this would be the indefinite integral of cosine to the 6th of y. So from the last slide, sine squared is the same thing as 1 minus cosine squared of y times sine of y dy. Now that you have rewritten everything in terms of cosine, you can set up your U-substitution. So I'm going to let u be cosine of y, and therefore du equals negative sine of y dy. Now that almost matches perfectly, but instead of getting sine y dy, we picked up a negative. That's okay. The extra negative you can just bring out in front of your integral. And then all of these cosines become u's. So it would be u to the 6th times 1 minus u squared du, where once again, I factored the negative out front. That way I could keep track of my du term. All right, so let's multiply the u to the 6th through. So this would be u to the 6th minus u to the 8th du. We can now integrate both of those terms, which would be u to the 7th over 7 minus u to the 9th over 9 plus c. And then I'm going to do two things here. I'm going to distribute that negative that we kept from the very beginning of the u sub to both terms, and you're going to plug your u back in. So your final answer should be the negative cosine to the 7th of y over 7 plus cosine to the 9th of y over 9, and then plus your arbitrary constant c. And that is how you would do the strategy of when one of your trig functions is odd, breaking off the term. All right. Occasionally, we will do definite integrals in this section, in these couple of sections, but not very often because these problems are a little bit uglier here. So what if you want to do the definite integral from 0 to pi over 2 of cosine to the 9th of x times sine to the 5th of x dx? Now, technically, both of these powers are odd, so it doesn't technically matter which one you break off, but I would always suggest, if that's the case, to break off the smaller power. So I'm going to leave cosine to the 9th of x alone, and I'm going to break one of my sines off to make it sine to the 4th of x times sine of x dx. And once again, you want this sine x dx to be your du term, which means I need to convert my sine to the 4th into a cosine term. Now, we do not have an identity for sine to the 4th, so you're going to have to do a little bit of manipulation here. So why don't we rewrite sine to the 4th as sine squared of x all squared times sine of x dx, because now I have an identity for sine squared that I can substitute in. This would be the integral from 0 to pi over 2 of cosine to the ninth of x. Sine squared from the last problem is 1 minus cosine squared, all squared, times sine of x dx. And now that everything else is in terms of cosine, I can now set up my U substitution. So I'm going to let U equal cosine of x, and therefore du would be negative sine x dx. Two things here. Number one, the du doesn't match exactly what we broke off. We have that extra negative again, but that's okay. You can just bring that negative out front. And since it is a definite integral, you need to plug your original parameters in for x and in the u function to get your new parameters. So if I plug in 0, cosine of 0 is 1, and cosine of pi over 2 is 0. Now those are backwards. We will fix that in just a second. Turning all of your cosines into u's, you should get u to the ninth times 1 minus u squared all squared times du, because you already brought the negative out front. You can flip this parameter around. If you bring another negative out front, since there's already a negative there, it will cancel with it, and you can actually write this as the positive integral from 0 to 1 of u to the ninth. And if you were to FOIL 1 minus u squared by itself, you would get 1 minus 2u squared plus u to the fourth du. Distribute that u to the ninth to all three terms, and you will get the integral from 0 to 1 of u to the ninth minus 2u to the 11th plus u to the 13th du. So on all three of those terms, we're going to add 1 to the power and divide by the power. So that's u to the 10th over 10 minus 2u to the 12th over 12 plus u to the 14 over 14, evaluated from 0 to 1. Now, if I plug my 1 parameter in, so plugging 1 in is not too bad, you should get 1/10. Now, 2/12 will simplify into 1/6, so that's minus 1/6 plus 1 over 14 minus, and then if you plug 0 into all three of those terms, all of those terms just become 0, so it doesn't really do much. Excuse me. You're going to need to find common denominators of these three fractions. So let's see, 10 and 6 and 14. I believe those all are going to go in. I think 210 is probably the smallest number they go into. We'll just play around with that. So I'm going to get a common denominator of 210. All right, so let's see. 10 goes into 210 21 times, so that would be 21 over 210. 6 goes into 210, let's see, 10, 20, 30, 35 times. And then 14 goes into 210, looks like 15 times. All right, and then if you combine all of your numerators here, 21 minus 35 is negative 14, and negative 14 plus 15 is 1. So your final answer is going to be 1 over 210. And that would be your final answer for this definite integral using sine and cosine. Once again, they're both odd, so you can break whichever one you want to off, but it's usually easier if you break the smallest power off first. All right. What if you have to use a different identity at the very beginning before you can figure out which strategy to use? So that's going to happen here in example number 3. What is the indefinite integral of sine squared x times the double angle of sine? Now, no strategy is going to work here because you don't have a sine times a cosine. You have a sine times a double angle of sine. So my first instinct here is, can I get rid of this double angle of sine? So from a trig class, and we reviewed this in a previous video, the double angle of sine is equal to 2 times sine x times cosine of x. I can directly substitute this identity in, and then I can combine terms to figure out which strategy to use. So this would become the indefinite integral of sine squared x times my double angle identity, which is 2 sine x cosine x dx. Now the extra 2 that you picked up is just a constant, so you can bring that out to the front. And then you're going to have a sine cubed of x times cosine x dx. Now, both of those are technically odd, so you could break whichever one you wanted to, but as you can tell, cosine is already an isolated term. So why don't we just let that term be our broken off piece, and we're going to set that up to be our du. That means that everything else has to be in terms of sine, which it already is. So I can actually go directly into my u substitution. I can let u equal sine x, and therefore du would be cosine of x dx. Substituting that information in, sine cubed would become u cubed, and just like we wanted to, those last two pieces become our du term. Add 1 to the power and divide by the power. So that would be u to the 4th over 4 plus c. Well, bringing the 1/4 out and combining it with the 2 will give you a 1/2. Substitute your u function back in. So that is sine to the 4th of x plus c. And that is your final answer for this indefinite integral. Just note that you can't do your strategies until you get sines and cosines in the problem. All right, and then the last thing we want to cover in this first part of section 7.2 is what happens when there are no odd powers of sine and cosine. So what about number 4? It is the integral of sine squared t times cosine to the 4th of t dt. All right, so the first thing we have to do is that there's not an odd power to break off. So strategy A and B don't work. Strategy C says, if both powers are even and they are the same power, we could use that variation of the double angle identity. That's not true here. One's a squared and one's a fourth. So the only way to attack this problem is we're going to have to use our half angle identities. But the half angle identities only exist if everything is a sine squared or a cosine squared. So I have to rewrite the cosine to the 4th of x as cosine squared all squared. And now I can substitute my half angle identity in for both of these. So this will be the indefinite integral of the half angle of sine from earlier is 1/2 times 1 minus cosine of 2t times the half angle of cosine is 1/2 times 1 plus cosine of 2t. All of that part needs to be squared. Now there are some constants that you pick up here, so let's isolate those first. You have this 1/2 that you could factor out in front of the integral, and then this 1/2 here is being squared. So 1/2 squared would be 1/4. And if this is a 1/4 and this is a 1/2, you can multiply those together and bring that constant out front. So I can actually write this as 1/8 times the integral of 1 minus cosine of 2t times 1 plus cosine of 2t all squared dt. All right, we got to multiply all this together. So the first thing I'm going to do is I'm going to FOIL the 1 plus cosine 2t together. So this would be 1/8 times the integral of 1 minus cosine of 2t times, if you were to FOIL this together and combine terms, you should get 1 plus 2 cosine of 2t plus cosine squared of 2t dt. And now you must multiply the binomial times the trinomial together and see what combines. So this would be 1/8 times the integral. So if I take the 1 and multiply it by all three of these terms, that would be 1 plus 2 cosine of 2t plus cosine squared of 2t. And then if I come back and take the negative cosine of 2t and multiply it by the three terms, you'll get minus cosine of 2t minus 2 cosine squared of 2t, and then minus cosine cubed of 2t dt. Now, a few of these terms do go together, so let's combine some like terms to make it a little bit better. First off, the only constant is 1, so I'll just leave that there. But you have a 2 cosine 2t and a minus cosine 2t, so those will combine into just a plus cosine 2t. Then you have a cosine squared minus a 2 cosine squared. Those go together as a negative cosine squared of 2t. And then you have the extra term of minus cosine cubed dt. Okay, 2t dt. Now, of those four terms, 2 of them we know how to integrate and 2 of them we do not. So going from left to right, if I were to rewrite this, this would be 1/8 times. I know how to integrate 1. That's just going to be t. I know how to integrate cosine 2t. That's just the anti-chain rule, which would be plus sine of 2t divided by 2. The last two terms cannot be integrated directly, so we're going to have to do some more work to solve those. But what I do notice is that both of them share a negative in common. So if I factor a negative in front of our integral, because I haven't integrated these last two terms yet, you get cosine squared 2t, apologies for that. Cosine squared 2t plus cosine cubed 2t dt. But remember, when you're done integrating these, you'll have the 1/8 you'll have to bring back through. Now, each of these two parts of the integral do not work the same way. So what I'm going to do, first one in red, is let's just integrate this part. So little scratch work here. If we are going to integrate cosine squared of 2t, that's going to mean you just have to do your half angle identity, because that's one of your strategies. If cosine is even and it's the only function, you can go straight into your half angle identity. Now, looking back up here at the top, earlier we did the half angle of cosine identity to get from cosine squared to its expanded form. Our difference now is that we're doing cosine squared of 2t. So in my identity, I have to double the angle. So in my identity, it won't be a 2t, it will actually be a 4t, because you have to adjust all of the values. So this would be the integral of 1/2 times 1 plus the cosine of 4t dt. I can factor that 1/2 out to the front, and then the two remaining terms, the 1 plus cosine 4t, I know how to integrate those two. 1 becomes t, and cosine 4t becomes sine of 4t over 4. And if I multiply the 1/2 through, this will be 1/2 t plus 1/8 sine of 4t. And so that's going to be the integral of just the cosine squared part. Now in blue, actually we'll do it in black here so it's a little easier to see for y'all on the screen. We now need to integrate just the cosine cubed term. So if I were to integrate cosine cubed of 2t dt, this is one of your strategies. Since cosine is odd, you can break off a cosine and set up a U-substitution. So this would be the indefinite integral of cosine squared 2t times the cosine of 2t dt. But if you want this term to be your du term, you have to make an identity for cosine squared 2t. Once again, adjusting our Pythagorean identity, cosine squared of 2t would be 1 minus the sine squared of 2t times cosine of 2t dt. Now that everything else is in terms of sine, I can do a U-substitution. So I'm going to let u equal the sine of 2t, and therefore du would be 2 cosine of 2t dt. All right. Since we picked up an extra 2, dt, sorry, technically when I bring this over, you have to think of this as being du over 2 cosine of 2t is dt. So when I substitute all of this in, it will be the indefinite integral of 1 minus u squared times du over 2 cosine of 2t. Well, very nicely. Oh, sorry, I forgot to put the extra cosine t. So there is, let me rewrite that. Sorry. This is times cosine 2t, then times my dt, which is du over 2 cosine 2t. My apologies for that. So the cosine 2t's cancel, and then you can factor that 1/2 out front and make this 1/2 times the integral of 1 minus u squared du. Integrate that, and it will be 1/2 times u minus u cubed over 3. Multiply the 1/2 through and put your u back into these terms. So it would be 1/2 times the sine of 2t minus 1/6 times the sine cubed of 2t. And so now we have officially found the two parts of the original integral. Now, once again, those are not your answer. Now, so big star at the top. We now must go back to our original problem. So now I'm going to go back to purple, and I need to substitute these values in for both parts of the integral. But do note that there is a minus in front of the integral. So this negative has to be applied to all of these terms when you put them back in. So bringing this part down to here, this would be 1/8 times t plus 1/2 sine of 2t. All right, so for the two red terms, distribute the negative to both of those. So that's minus 1/2 t minus 1/8 sine of 4t. Then also distribute the negative to the two parts in black here. That would be minus 1/2 sine of 2t plus 1/6 sine cubed of 2t. And now that I'm officially done integrating this problem and that it's indefinite, don't forget, now you have a plus c to worry about. Now, some of these terms go together, and even I see a pair that actually cancel. The 1/2 sine of 2t and the negative 1/2 sine of 2t cancel, and then you can put your t terms together, and this would give us 1/8 times t minus half of t would just be half a t minus 1/8 sine of 4t plus the 1/6 sine cubed of 2t plus c. And last but not least, distribute the 1/8 through and you will be done with this problem. Your final answer is 1/16t minus 1/64 sine of 4t plus 1/48 sine cubed of 2t plus c. This is your final result. But as you can see, when the powers are even, that's the strategy that doesn't work out as nice because there's a lot of identities and there's a lot of substituting in the process. But that's how you will approach when both powers are even for sine and cosine. So now we're going to move into our second strategy here. So we're going to move away from sine and cosines for the time being. The next strategy is how do you how do you integrate a tangent function times a secant function based on the powers of tangent and secant? So the good thing is that there are only two rules here, and if it doesn't fit one of these two rules, we're not going to be able to work it. So the first rule is if the power of secant is even, then what you want to do is break off or save a factor of sine squared, and then you will have to use the identity secant squared equals 1 plus tangent squared to express the remaining factors in terms of tangent. So once again, kind of showing you the mathematical here. If secant is even, you would break off a secant squared to make that your du term. All of the remaining secants have to be converted into tangents by using the identity above, and then you would let u equal tangent of x in order to set up your u sub, because the derivative of tangent is secant squared. So if secant is even, you break a secant squared off, rewrite everything in terms of tangent, and set up a u substitution. The other strategy is not the same. It's completely opposite. What if we move to tangent, but tangent has to be odd for this strategy to work? You would instead break off a factor of secant and tangent. So you need one of each. Then you would have to use the identity tangent squared equals secant squared minus 1 to rewrite everything in terms of secant so that you can set up a u substitution. So you can see in our strategy down here, if you break off the secant tangent, which is going to be my du term, then I have to rewrite all of the tangents in terms of secants using the above identity. Then you can let u equal secant and set up your u substitution, because the derivative of secant is secant tangent, and that will allow the broken off part to be your du term. These are the only two strategies that have to do with tangent and secant. If secant is even, break off secant squared. If tangent is odd, break off secant and tangent. If it's both, you can do either one. Once again, I would focus on the smaller power there. And if you have an even tangent and an odd secant, that's not something we know how to do just yet. We'll get into that into a later section. So let's look at some examples of how to approach the strategies of secant times tangent. So if you have the indefinite integral of tangent to the fourth times secant to the sixth. So thinking over your two strategies, secant even, tangent odd. Well, in this strategy, the only one that applies is secant being even. So when secant is an even power, our strategy tells us to break off two of your secants, and we can rewrite the last part as secant to the fourth times secant squared. And you want this secant squared part to eventually be your du term, which means I need everything else to be written in terms of tangent. Well, tangent to the fourth is good. I need to rewrite secant to the fourth. So I would first rewrite this because I don't have an identity for secant to the fourth. This would be tangent to the fourth of x. And like we saw in the sine and cosine problems, I can rewrite that as secant squared all squared times secant squared x dx. And we have an identity for secant squared, excuse me, as being 1 plus tangent squared. So this is the indefinite integral of tangent to the fourth of x times 1 plus tangent squared x all squared times secant squared x dx. Now I can set up my u substitution. So I'm going to let u equal tangent of x, and therefore du is going to equal secant squared of x dx, just like I wanted it to. So this would become the indefinite integral of u to the fourth times 1 plus u squared all squared times du. You need to FOIL the 1 plus u squared by itself, When you do that and combine like terms, you should get 1 plus 2u squared plus u to the fourth du. I now can distribute this u to the fourth to all three terms, which will be u to the fourth plus 2u to the sixth plus u to the eighth du. And finally, I now can integrate this function. This will become u to the fifth over 5 plus 2u to the seventh over 7 plus u to the ninth over 9 plus a constant c. And now finally, you go back and substitute your u back into all three of those. And your final answer is tangent to the fifth of x over 5 plus 2 times tangent to the seventh of x over 7 plus tangent to the ninth of x over 9 plus an arbitrary constant c. And that is how you integrate the previous problem. So that is how you would work if secant was an even power. But I also want to show you the other strategy as well. So strategy B says, what if tangent is odd? So this problem, we're going to do what is the integral of tangent to the fifth of x times secant cubed of x. So since secant is not even, we can't do strategy A. We're going to have to use the second strategy that says if tangent is odd, you have to break one secant and one tangent off to the end. So we would actually rewrite this as tangent to the fourth of x times secant squared of x, and then the extra secant and tangent will go on the end. Eventually, you want this to be your du term. The only way that will work is if everything else in the problem is in terms of secant. So the secant squared is good, but you're going to have to rewrite the tangent to the fourth. Because first off, I don't have an identity for tangent to the fourth. So I'm going to rewrite that as, oops, that's bad handwriting. I'm going to rewrite that as tangent squared of x, all squared, times secant squared of x, times secant x, tangent x, dx. From earlier, a couple of slides ago, the identity for tangent squared can be written as secant squared x minus 1 all squared times secant squared of x times secant x, tangent of x, dx. Now that everything else is in terms of secant besides my du term, I can now set up my U-substitution. I'm going to let u equal secant, and therefore du would be secant of x, tangent of x, dx, just like I wanted it to. So this will become the indefinite integral of u squared minus 1 all squared times another u squared times my du term. I need to FOIL the u squared minus 1, which will give me u to the fourth minus 2u squared plus 1 times another u squared du. We can then distribute that u squared to all three terms, which will make this the integral from u to the sixth minus 2u to the fourth plus u squared du. And finally, you can add 1 to the power and divide by the power. So this is u to the seventh over 7 minus 2u to the fifth over 5 plus u cubed over 3 plus a constant c. And now you want to substitute your u back in. So this will become secant to the seventh of x over 7 minus 2 secant to the fifth of x over 5 plus secant cubed of x over 3 plus a constant c. And that is your final answer. And that is how you do the strategy of when tangent is odd. Now that we have learned a couple of new integration techniques, we can now go back to some topics that we covered in earlier videos and now apply some new problems. So let's go back in section 6.1 when we did area between curves. So let's do a new one that we can now actually solve. I want you to find the area of the region bounded by the given curves y equals sine squared and y equals sine cubed on the interval 0 to pi. So if you look over here at the graph that's given, it's very easy to see that the red graph is always above the blue graph as you go from left to right. So therefore, it's always going to be the same top minus bottom function that we discussed back in 6.1. So while labeling these, it's easy to see that the red graph here is going to be sine squared, and the blue graph here is going to be sine cubed of x. So when I set up my integral here, so remember back in 6.1, area between curves, you would integrate from a to b, which we're going to go all the way from 0 to pi, of your top function, which is sine squared of x, minus your bottom function, which is sine cubed of x dx. Now, similar to the problem earlier that we did, each of these integrates a little bit differently. So what I'm actually going to do is I'm going to integrate each one separately and then put my final results together. So I'm going to match them to the colors of the graphs actually over here. So the first thing I'm going to do is I'm going to integrate from 0 to pi of just the sine squared function. This is one where you can just use your half angle identity. So this would be the integral from 0 to pi of 1/2 times 1 minus the cosine of 2x dx. I can factor the 1/2 out front, and then I'm able to just integrate the two functions inside of the parentheses, which would integrate into x minus the sine of 2x over 2, and I'm going to evaluate this from 0 to pi. All right, so if I plug pi into both of those values, that would be pi minus sine of 2 pi is 0, so that whole term goes to 0, minus, and then if you plug 0 into both of these, they both become 0. So with 3 of your 4 terms going to 0 here, all you have to do is multiply the 1/2 times pi. So the area of the first part of the original is pi over 2. All right, so now in blue, I need to integrate from 0 to pi of sine cubed of x dx. Now, since sine is odd here, you can use your strategy from the very beginning of this video and you can break off one of your sine terms. So this would be the integral from 0 to pi of sine squared x times sine x dx. Remember, you want this term that you broke off. That needs to be your du term. So I need to rewrite sine squared in terms of cosine. So that would be the integral from 0 to pi of 1 minus cosine squared of x times sine of x dx. And I can now set up my U-substitution. So u is going to equal cosine of x, and du is going to be negative sine of x dx. So two things here. Number one, we're really close to the du, but you picked up a negative here, so I can just bring that negative out in front of the integral. You need to change your parameters because you're doing u sub. So if I plug 0 in, cosine of 0 is 1, and the cosine of pi is negative 1. And then inside the integral, you're going to have 1 minus u squared du. All right, I'm going to flip those parameters around just because I feel like it's a little bit easier to follow. So if I do that, I can bring an extra negative out front, which will cancel the negative I already have out there. And then if I integrate, and then you have 1 minus u squared du. So now you can integrate this directly. This would be u minus u cubed over 3 evaluated from -1 to 1. So by plugging 1 in, you will get 1 minus 1/3, minus, if you plug -1 in, you get -1 minus a -1/3. All right, so that would actually become 1 minus 1/3. If you distribute this -1 to both terms, it will be +1. Since this double negative makes it positive, and then you multiply a negative through, it'll actually be -1/3 as well. 1 plus 1 is 2, minus, combine the thirds to get 2/3, and 2 minus 2/3 is 4/3. But now you have to go all the way back to the beginning. So this original integral here, if you plug your pieces in, the integral of sine squared part was pi over 2. Then you must subtract the integral part of sine cubed, which was 4/3. So your final area between these two curves is pi over 2 minus 4/3. So that is how we can now start doing problems that we couldn't cover earlier. So we're bringing back old topics and applying new ideas to these problems. All right, so we did area. You can also do some more volume problems that we did back in section 6.2 and 6.3. So this example says, find the volume obtained by rotating the region bounded by the curve y equals cosine x and y equals 0 between the interval 3 pi over 2 and 2 pi about the x-axis. So we want to take this black shaded region right here, and I want to rotate it around the x-axis. Now, since there's not a gap there, the most direct way to do this will be to do this using the dis method that we covered in section 6.2. So recall that the dis method is pi times the integral from a to b of your radius function squared. And since we're going around the x-axis, it'll be respect to x. All right, so now plug in your information. This would be pi times the integral from 3 pi over 2 to 2 pi. Square your function. So the curve that you're rotating here is cosine. So this would be cosine squared of x dx. And now it becomes one of the strategies we discussed in this section. All right, use your half angle identity. So this would be pi times the integral from 3 pi over 2 to 2 pi. And the half angle of cosine is 1/2 times 1 plus cosine 2x dx. I can factor that 1/2 out front to make it a pi over 2. And then I can just integrate the two terms inside the parentheses, which would be x plus the sine of 2x over 2, evaluated from 3 pi over 2 to 2 pi. All right, so this would be pi over 2 times, if I plug 2 pi into both of these values, that would be 2 pi plus sine of 4 pi is 0, so that term goes away, minus, then you get 3 pi over 2 plus, if you double 3 pi over 2, that's 3 pi, but the sine of 3 pi is still going to be 0. If you combine your angles inside the bracket, you're going to have the 2 pi minus the 3 pi over 2, which is just pi over 2. And when you multiply these two terms together, you get a final volume of pi squared divided by 4. So that's how we brought back the dis method from 6.2 and applied it to the new techniques that we've learned today. That ends the video for section 7.2, and that was trigonometric integrals. Please make sure you understand these ideas, because in the next video, which is another trig section, this is going to be part of what we have to do in the next technique we're about to learn. But I'll see you in the next video.